All right. So after a short break, it looks like the last stream got stuck, and we are slowly moving forward. I got a question what this number 3 here means. It means how many questions that were posed directly to me about the things I stream about or cover in my classes. I actually answered on stream. Every time I answer a question, I push a button and I get an extra point. It's a motivational thing for me. So if we consider this done, let's talk about counting. So how are we going to do about this? Let's see. Let's go. All right. So when we talk about counting, we want to talk about the possibilities of things. And we're going to start by looking at the fundamental counting rule. So the fundamental counting rule says the following, that if you have an event that can occur m ways. For example, flipping a coin can the event of getting a face on a coin, you can get either heads or tails. So there's two ways to do it, right? And another event that can occur n ways. Rolling a die, there's 6 ways that you can produce the outcomes, or drawing a card, and there's 52 cards in a deck. Then together they can occur m times n ways. Well, let's look at an example. If you flip 2 coins, what do we have? Well, coin number 1, we can get heads or tails. Coin number 2, we can get heads or tails, right? So there's 2 ways this event can occur, and there's 2 ways here. So together, right, those 2 coin flips can occur 4 ways, right? 2 times 2. If we draw a card, there's 52 cards, or there's 52 choices, and you flip a coin, that's 2. Together you can get 104 ways this can do. The reason why we're looking at this, we're looking at all the possibilities. All right, let's look at something bigger. Your credit card, right, has a CRV code in the back. It's CVR, CRV. There's a code on the back of your credit card, right? This little number right here. So there's 3 digits. So assuming I stole your credit card, right? I stole your credit card number and your name and your billing addresses. If I want to go on Etsy on a shopping spree, most of the times I need this code. I don't know it, right? I just stole the front of your card, right? I stole the front of your card, not the back of your card. So, well, let's see. I have It's a 3-digit number, right? And I have a bunch of options. How many options do I have for the first one? Well, it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 options here. Second number, still 10 options. Third number, 10 options. Which means that altogether there's 1,000 options for it. So if I was going to guess which one is right, that's probability of getting it one of those numbers being right out of 1,000, right? And we can expand this. Your iPhone or your smartphone has a 6-digit code. Each one of those digits can be from 0 to 9, so there's 10 possibilities, right? So 10 times 10 times 10 times 10, we have 1,000,000 choices, which is great, right? So this is the basic application of fundamental counting. So let's look at something different. Let's look at cards. Let's get an ace here first. Right. So let's look at cards. We have ace, 2, 3, 4, and 5. That. So we have 5 cards, and my question is, how can we arrange those? Well, what do I mean by arrangement? This is one arrangement. This is another one, right? That would be an arrangement, right? We have several choices for those arrangements. And there's another one, and another one, and another one, and another one, and so on and so forth. So my question is, how many are there? How many of those arrangements, how many of those different arrangements can I do? Because eventually I am going to reach a point where what I have is exactly what I had to begin with. Right, so we have 5 cards. 5, 4, 3, 2, and an ace. Right, all of them spades, just to make it simple. So how many? Well, let's see. We have 1, 2, 3, 4, 5. Without caring about what the front is, let's look at the back. I have 5 cards. I have to pick a card for the first slot. Well, how many choices do I have? 1, 2, 3, 4, 5. Well, I'm going to pick one. Whatever it is. 5. How many choices do I have for the second place? Well, there's 4 cards left, so 4. How about now? Well, the 3 cards. 3. Then I have 2. And then finally, I have to pick. And then finally I'm left with 1 card, and 1 card is not a choice. Having 1 option is not a choice, but I put a 1 here. Looking at the fundamental counting rule, it tells us that if something happen m and n ways, together they're multiplied. This can be expanded to something m, n, o, p, and q, and r, and whatnot. So all of it is multiplied. So if you multiply all of this out, we got 120 permutations, right? So this is 120 permutations of 5 unique items. And then I'm going to call it items or objects, right? What does permutation mean? Well, different arrangements. Okay, this is cool. Well, the problem is, what happens if I decide to, make it more fun, and I say, hey, how many arrangements are there of this? It's a lot of cards, right? There's just plenty of them. well, I could count them and I could make my low bars and I could, you know, tell you how many are in the first one, -1 in the second one, minus. Just seems tedious. And I don't know about you guys, but I feel a little lazy. I've been fighting with YouTube all morning, so I'm kind of overdoing this. So let's look at back to our 5-card thing. So if we have those 5 cards, we can do this. That's easy. But maybe there's a method for us to compress this into something else. And there is. In math, we have a notation that contains all of this, and that's 5 with an exclamation point. This exclamation point is factorial. Depending on the calculator you have, in case of those TI-30s, it's under the probability button right here. Right, you push probability and there it is, right on the side. So under probability. Yeah. So you go 5 probability, scroll over to exclamation point, bam. And there's plenty of online calculators and Excel can handle it and whatnot. So there's a bunch of ways to do it. And this just means, right, 5 factorial. 5 times 4 times 3 times 2 times 1. Which is that for a set, any set of n different and unique items, there are n factorial different arrangements possible, right? If we had 8 objects and they have to be unique, right? 8 people would be unique. Then we can arrange those 8 objects in 8 spaces, right? In 8 factorial ways. Well, again, if we just do this little thing, this is 40,320 ways. Great. So here's a little definition we should kind of introduce, and that's 0 factorial. Okay, how do we deal with this? If it's a bigger number, right? 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, so all of this is easy. How about we do 0 factorial? What does it mean? Well, 0 factorial means we are asking how many arrangements, unique arrangements, can you do of 0 objects? Or if you want to be crude about it, how many ways can you tell your girlfriend you love her if you don't have a girlfriend? Well, 1 way. You go to the fridge, you pick up a jar of Haagen-Dazs and you cuddle that for the rest of the night. Right, it's kind of absurd. How many ways can you deal 0 cards? Well, 0 way. No, not 0. 1 way. You just don't do it, right? How many ways can you clean a room that you don't have? How many ways can you pick a car in your garage if you don't own cars? 1 way. So this is 1, not 0, 1. And that's important. Alright, so this is the very basics. So let's expand. If we talk about those arrangements, those unique arrangements, what happens if we don't care? What happens if out of, say, 7 cards, this is getting awfully close to Texas Hold'em, but out of 7 cards, you only care about the first 5, right? You have 7 cards and you care about the arrangement of only 5 of them. So there are 7 cards. how many ways can you pick 5 of them? If your instinct is to go, well, 5 factorial this way, you're going to be wrong, because there's 2 extra cards to pick from. So the first time around, I'm going to pick 1, right, then 2. So 1, 2, 3, 4, 5, right, picking 5 cards. For the first one, we have 7 choices. Second one, 6. Third one, 5, 4, 3. And you multiply this out. This number is going to be obviously bigger than this number. Great. This is starting to get big, right? Again, if I toss a bunch of other cards into this mix or a bunch of other objects into this mix, this gets really big. So is there a way we can look at it? Well, we could. This multiplication, if we multiplied it times 2 times 1, this would be just 7 factorial. But this 7 factorial is losing this end tail. We don't care about the last 2 cards. We just care about the first 5, right? So we don't care about the back. So how do we get rid of this? Well, we could divide it out. If we divided the whole thing by 2 factorial, right? Well, what is 2 factorial? It's 7 minus 5, right? Out of the 7, we take only the 5. And then there's factorial. Okay? And this is the basis for a formula for permutations. So if we are talking about permutations, we are talking about a setup that has n different items. We gotta start somewhere, right? Out of this set, we're gonna pick our items to be arranged. Well, so out of 7 we picked 5. That's our R. And then we need to understand that the arrangement matters, right? Or the order of those cards matters. So it matters that I pick this one first, second, third, fourth, and fifth. And for this setup, right, we get n factorial, right? 7 was our n, divided by 7 minus 5, right? Factorial. And this is NPR. And again, your calculator, the TI-30 has it on the probability. Some other calculators have it over, I think, number 3 or 5. So you just have to take a look at it. If you cannot find it on your calculator, just take a picture of the face of your calculator, and I will find it either on it or I will look up the manual and help you find it. But you can also do this online. Calculating permutations is available. As long as you know how to do it on paper, for homework's sake, you're more than welcome to use online calculators. One little caveat, on the final, you're going to have to deal with this. Alright, so how do we deal with this? Well, we say 7p5. In our case, that would look like 7 probability, press enter, 5. Right, and then we press, and that comes out to be 2520. Now let's check if this number is correct, and I'm going to go 7 times 6 times 5 times 4 times 3. Yep, same thing. It works. So this is permutations. What else can we do? We could, aside of cards, we could pick people into school governments, right? If there is 11 kids, how many how many ways can you pick president, VP, and secretary? Well, let's see. It matters which one is which, right? So we have 11 kids and we're picking 3. Order matters, right? We want to pick the president first. Well, so it's 11p3. And again, we can very easily do this on a calculator. We should get an answer 990. All right, so this is kind of the basics. All right, so next question. What about the following situation? Let's say we have 10 objects and they look like this, right? Those are 10 objects. So what do we think? We're thinking, well, there's 10 factorial arrangements. If you want to arrange 10 objects into 10 places, ta-dam, right? When we're done. The problem is, how will you know the difference between each one of those squares or each one of those circles or each one of those triangles? That runs into a problem. And here, I would like to introduce you to Billy, Bob, and James. Billy, Bob, and James is an invention of mine that I've been using to try to show this. And Billy, Bob, and James, well, it's high school time, so they're all squares. Billy, Bob, and James. And Billy, Bob, and James decide to join their friends. Oh, it's getting windy. Billy, Bob, and James decided to join their friends to go trick-or-treating. And my question is, how many ways can 10 people come into my door to get trick-or-treats? If we just looked at Billy, Bob, and James, right, that's 3 individuals. If we arrange them in 3 spaces, that's 3 factorial ways we can do it. So there's 6 ways we can arrange them. Oh, so we could go Billy, James, Bob. We could go Bob, Billy, James. We could go Bob, James, Billy, and James, Bob, Billy, and Billy, Bob. And there's my 6 arrangements. 1, 2, 3, 4, 5, 6. So far, good. What happens in Halloween? Those arrangements, right? Those 6 arrangements that we have, all end up wearing a sheet, right? They're all squares, so invention and creativity is lacking. So 3 of them dress up the same way. They put a sheet over their head and pretend to be a ghost. And so from the outside perspective, regardless of how they arrange themselves, all I'm seeing is 3 white squares, right? I had distinction, now I don't. Right? So out of 3 factorial arrangements, since all of those are exactly the same, I have 1. Right? I lost a piece of information, and I don't know if Billy, Bob, or James came to my door first. which means that if we're looking at this problem, if we're looking at this problem, this 10 factorial setup suddenly lost 3 factorial resolution. I lost some information, which means then suddenly those 3 arrangements are looking very different, right? This arrangement and this arrangement are different, and so is this one, right? And I can build all 6 of them. How about now? Ready? Don't blink. Don't blink. Is this an arrangement we already had, or is this a new arrangement? Well, since you're looking at the back of the cards, all of the cards presumably are the same, which means that this and this is the same arrangement, which means that if in a grand scheme of things, I lost that arrangement. So this is this 3 factorial, right? If I looked at this, how many arrangements can I do? Well, can I do this one, or this one, right? I can only do 3 arrangements because this doesn't matter. And so how do we justify this? Well, we justify that we lost arrangement for this. How about the circles? We can't tell the difference between circles, so we lost 2 factorial arrangement. Why 2 factorial? Because there were 2 objects that were supposedly unique, but they're not distinguishable now. And then there's 5 factorial for the triangles. Now, if you're answering question in my class, I'm happy with this as an answer. If you want to expand it, either a calculator or you have to do it by hand. And I'm going to do it by hand because that's going to be faster. Right? Because it's 5 times 4 times 3 times 2 times 1, and that's 5 factorial. And divided by 3 factorial times 2 factorial times 5 factorial. Well, 5 factorial here, 5 factorial, check. What is 3 factorial times 2 factorial? That's 3 times 2 times 1 times 2 times 1. Well, 3 times 2 times 1, that's 6. And then 2 and 8, that's a 4. So what I'm ending up with is 10 times 9 times 4 times 7. It's 90 times 28, 240, 250, 252. Right? Again, if we were just looking at 10 factorial, that number would be huge. But because we have pieces of it that don't behave like unique objects, we lose that as a resolution. Right? So when we have non-distinct items, we have less unique arrangements. One of the very cool thing about it is if you play, for example, with words, how many ways can you arrange the greatest 10-letter word in English language? Statistics. Well, there's 10 letters, 10 factorial. But there's 3 t's, so we lose 3 factorial resolution for t's. There's 3 s's, so we lose the resolution for that. There's 1 a, 1 factorial is 1, so I'm not worrying about it. There's 2 i's, s's, and then there's 1 c. So if you really want to do 1 factorial for a, and then times 1 factorial for c. 3 plus 3, 6, 7, 8, 9, 10. And we can calculate this, and if you really 1 to that comes out to be 50,400 words. Of course, they're not all meaningful words because those are just arrangements of letters, but there you have it. Let's try one more. At a bar, there is 7 draft beers and 6 snacks or pupus to choose from. Right? If you want to sit down and have a beer and a snack, how many different ways can you do it? For those of you who are old enough to go into bars, it's going to ruin it. You can do statistics in bars. So let's take a look at, well, there's 13 choices altogether. But, right, you really want a beer and a snack. So we don't care what beer we have, and we don't care what snack we have. We just want a beer and a snack. Well, there it is. Right? Because you could have a beer and another beer and another beer, and then all the snacks and then the rest of the beers, right? How many different ways can we put this together? Right? When I say here, just so we avoid the confusion, when I say here beer and a snack, I mean you want to eat it all. Right? You want to have all of it. Like you want to have all the beers and all the snacks. Well, how many ways you can eat it? Well, eat a beer and a snack. Well, one beer and one snack. Well, how do you pick one beer and a snack? If you want to eat it all, then this. How about if you want to have only one beer and one snack? What then? We're gonna get to this because this is the cool part of this. Let's consider the following. Let's consider that we're back to our 7 cards. Right? We're back to our 7 cards. We're back to the 7 cards. And we pick 5. But we don't care about order. What does this look like? Well, can you pick 5 cards? 5 cards. I don't know which one I picked first, which one I picked last. I just picked 5 cards, right? The difference between the permutations that we do beginning is like, that's number 1, that's number 2, that's number 3, that's number 4, and that's number 5. When we're talking about combinations, there's the 5. Right? So how do we do this? Well, we have to pick out of the 7, 1, 2, 3, 4, 5, 6, 7. Out of the 7, we're gonna pick those 5. That's the 5 out of the 7 total that we had. We're gonna pick those 5. But because we don't care about the order, can we distinguish right? We don't care about the order. Can we distinguish between picking them like this or picking them like this? Well, we can't, right? So we lose this distinction of how do we those 5 cards got arranged. We just pick them up as a whole. And this brings us to combinations. How do we pick combinations? Well, combinations look very similar. Well, first of all, you have to have n different items. 2, you need to select r of them, just like before. And 3, arrangement doesn't matter. Now, what does it mean? Well, A, B, C is same as B, A, C. Those two things are exactly the same, right? Billy, Bob, and James kind of. And for that, well, we start the same way we started before. That's permutations. But now that R section of it, the first 5 that we want to do, we lose that resolution. And to lose that resolution, we divide by R factorial. This R, this thing, removes the distinction of those R items. Why do you mean distinction? Well, because if we knew what the cards was, moving the red card or the queen around is very, very visible. But how about now? Can you tell the difference? And blink, right? So this is what I mean. If I don't care about the order, this. If I care about the orders, this is different than this. Right? So this is the idea behind it. And that has a symbol, NCR, right? R objects arranged out of N objects when we don't care about the order. Alright, so let's look at this one. If we want to have it all, this is it. But if I want to have only 1 beer and 1 snack, I am picking out of 7 beers, I'm picking 1. And out of 6 snacks, I'm picking 1. That's what combinations would look like. The problem of this problem is very easy, because if you're picking 1 out of 7 beers, you have 7 choices. Picking 1 out of 6 snacks, you have 6 choices. So that comes out to be 42, and we're done. So this seems like a long way to do it. But what happens if out of 7 beers, you pick 5, and out of 6 snacks, you pick 2? Well, then it becomes 7C5 times 6C2. Okay? If you want it all, there it is, all of them. If you want it all, that's all of them. And again, the solution for having all of the snacks, well, what is it? Well, there's 13 snacks, right? And you just don't care about the beers and this. This is the lost of it, right? If you're picking 13 out of 13, if we care about the order, this is it, right? And that comes out to be 13 factorial divided by 13 minus 13 factorial. And that's all this. And this comes out, this is 0 factorial, which is 1, right? So this comes out to be 13 factorial. So that's the top part. And now we just chop off the resolution, which is We don't care about which beer and we don't care about which snack. This is for all of them. But if you have a beer and a snack, then we're talking about smaller sections. And this should help this should help you with with questions 8 and with big chunks of question 1. Okay, so this is what counting looks like. It's exactly that. It's just a slow process of trying to sort out how many options do we have. Because if we can figure out how many options do we have, we can do a lot of really cool things with probability. And that should close out chapter 2. At least kind of a shortcut through it. Now again, if you guys need, want, or desire more practice problems, I'll be happy to put something together for you guys, for you to do. If you want to solve some problems you found somewhere else, just post a link to the problems or like a screenshot, or copy and paste the problems into a forum post and then a solution. And if one of your fellow students attempts to help you with that, more points to them and more glory too. Otherwise, I'll gladly help you. The whole idea behind statistics is practice, 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 and well, there's nothing else to it. Again, chapter 1, which is the probability, is a mixture of things, mostly designed to help you see probability and numbers as something you can easily do with before we get to chapter 3, which is the actual extension of the probability. So that covers chapter 1, and then I will do my best to give you guys a kind of a overview of chapter 2. I feel like I'm talking to myself. All right, well, this is it. Let me know, and then the next Q&A is next Tuesday, 10 a.m. Hawaiian Standard Time. So if you have any questions, just post them to up to Monday night, and I'll do my best to answer them. If you have homework questions, just let me know. I'll attempt to solve problems that look very similar, so you get a feel for it. And on that note, have a great Tuesday, guys.